Good morning. Today I thought actually we have to go to the second chapter, but I thought I will refresh your memory about the first chapter first, and then we go to the second one. So in this last class we talked about experiments, right? Experimental studies. As I told you in the last class, especially when you are collecting data, there are two methods. That is experimental studies and observational studies. Experimental studies and observational studies. These two differ mainly on one factor, that is whether you have any control over who is going to get the treatments and who is not going to get the treatment. That is the main factor that separates these two types of studies. In experimental studies, usually there are some variables that you want to study, and there is maybe again one or more variables. You want to look at the relationships, whether one is depending on the other one, whether one is causing the other one, and so on. So in that case, especially if you want to look at the causation, whether one or more variables are causing the changes in another variable, you have to actually carry out experimental studies. Right? Otherwise, we will discuss in the next chapter that in observational studies, it's difficult to talk about causation. Right? So there we learned a few words. So let us discuss again about those words, just to remember, see whether you remember the differences and similarities. So what is the control? When you say control, there are several meanings. One meaning is what? Control. When you talk about control, you use the word control to refer to a unit or a person who is getting the treatment, for example. That is one meaning of that, right? So unit is called a control. So controlled experiment is where you have some control over which units are going to which individuals or units or animals or whatever, right, entities are getting the treatment and which are not getting the treatment. That is what we mean by controlled. And of course, you later on randomize, otherwise there will be again it will be a type of observational study. But control means you have some control over who is going to get the treatment and who is not going to get the treatment. So therefore, obviously in an experimental study, there is a treatment group and a control group. Right? In that case, control group means those who are not getting the treatment. The treatment group is the set of people who are getting the treatment, or maybe it is exposure. This word treatment is usually used in experimental settings, but in observational settings also you can have these two groups, but in that case usually we use the word exposure instead of treatment. Right? For example, whether you are exposed to smoking, and when people will go to find out whether smoking is associated with lung cancer, for example. In the case, the word, the more commonly used word is exposure than the treatment. Right? So when you talk about treatments, then we are interested in what is the effect of treatment. Right? So the treatment effect can be defined in various ways. One commonly used method is to look at, for example, if you are observing some variable for the two groups, you look at the mean of that variable for the treatment group and you look at the mean of the variable for the control group and then look at the difference. Right? So usually that is one way to define the treatment effect. Right? The difference between these two, difference between the means of response variable is termed as the treatment effect. That is one way to define. Or in the for example, Salk vaccine experiment, it was not the mean we were looking at incidence ratio it's a proportion of people who get polio and proportion of people who didn't get polio. So in that case, one might define the difference between the proportions in the two groups as the effect of the vaccine. Right? So you have to define what you mean by the treatment effect. So those are two commonly used methods. In some other methods, there are different ways. Right? So when you have controlled experiments, it's natural to have give the treatment to the exposure to the treatment group, but then the other group has to be given something, otherwise that's going to be a problem. So therefore, usually we use something called placebo. Right? So that sounds very similar to the treatment, but it doesn't have any effect. Right? So something that is similar to the treatment but without any effect is called the placebo. So there is another word called placebo effect also. The placebo effect is not actually the effect of the placebo, right? Because the word sometimes implies that it is the effect of the placebo. Placebo effect is not the effect of the placebo, it is actually kind of a mental effect, right? Especially when the people don't know whether they are getting the treatment or not, right? So everybody is thinking that we are getting the treatment, right? So then they have some kind of psychological effect, because they are thinking that they are getting a treatment, right? So it is completely different from the actual treatment effect, right? Even without the effect, people have seen that some people get improvement. For example, they have seen that after some operations, right? Some people are given a painkiller, some people are given a placebo. Right? So even people who get the placebo, some proportion improves, so they get some relief. So that is not because of the treatment. So that is because of some psychological effect, that thinking they are getting the treatment. Right? So the same effect will occur in the people who are getting the treatment also, because they don't know. Nobody knows whether they are getting a placebo or not. So they are all thinking that they are getting the treatment. So just because of that idea or the expectation, there can be some effect. That effect is called the placebo effect. So the next word we learned was randomized controlled experiments. You already know why we call it controlled. Right? Once we have decided which group is going to get the treatment and which group is going to get the placebo, how do we decide that? We divide the population of interest, or maybe a sample of interest, and then we divide the sample or the eligible people. We divide them into two groups using some kind of randomization. Right? So you have to use a coin tossing method at least, or maybe you have to put some numbers or names into a hat and pick up these numbers randomly and divide them into like that. There are so many random mechanisms that you can use in these days. Right? So you have to randomly divide the eligible participants into two groups, and then again randomly decide which group is going to get the treatment and which group is going to get the placebo. That is also randomly decided. Again, you can use a coin toss. So that is what we call the randomized controlled experiment. Sometimes there are experiments where they are controlled experiment but not randomized. There are two groups, but the treatment is given to a specific group. It's not randomized. We will look at some examples here. And then double-blind design. Right? What do you mean by double-blind? Double-blind means one blinding is placebo and treatment, right? So the participant don't know whether they are getting the placebo or the treatment. So that is one layer of blinding. And the other layer of blinding is after the experiment, somebody has to decide whether this person has this particular condition, for example, polio, whether he has polio symptoms or not. That has to be done by a doctor. So the doctor doesn't know whether this person has got the treatment or not. So that is the second layer of blindness. So that kind of experiment with those both kind of blindness is called double blindness. The next word is bias, and then the confounding. So bias is actually now, if you are, for example, looking at the effect of the polio vaccine, there is some effect which we really don't know the amount. The amount is unknown, but there is some value. So by using some experiment, we can estimate that effect. As for example, we define, for example, effect to be the mean, difference between the means in the two groups. Right? So here when we talk about the mean, what we mean by actually the population. So the treatment effect can be defined as the mean of whatever, for example, the proportion in this mean, not the mean, the proportion of people who would get polio if they are in the treatment group or if they are given the vaccine. So that is an unknown quantity. Right? The population proportion of people who would get polio if they are given the polio vaccine. Right? Then we can consider population proportion of people who will have polio if they don't get polio vaccine. So these two quantities are unknown quantities. They are population proportions, and actually they are kind of imaginary values. But they are there. We can imagine that there will be some values like that. If we give the polio to the whole population, some people will get polio vaccine to the whole population. Some people still will get polio. Some people will not get polio. So there is a proportion of people who would get polio. In the other group, if you assume that nobody is given the polio, then you can assume that there will be some proportion of people who will get the polio. So there will be the difference between these two can be defined, for example, as the actual treatment effect. Actual treatment. So what we want to find out is that the actual value. That is what we really want, if possible. But unfortunately, it's not possible to find out the actual value because we are not going to consider the whole population, and then we cannot actually do this experiment like that. We can only imagine that there is a value. But that is the quantity that we are interested in. Right? So what we do is actually we select a sample of people and then divide it into two, and then one group get the treatment, the other don't get the treatment. And then we can find out the sample proportion of people who got polio in the treatment group, and also we can find out the sample proportion in the other group, and then we can find out the difference. So that can be observed, that is an observed value. So that observed value we consider as an estimate or an educated guess for the actual quantity that you want to find out. So that is going to be only an approximate value. It's an educated guess because we have done some experiment in the correct way, and then we have got some values. So it's not just a wild guess, it's a scientific guess. So we are going to use that as an estimate, we say. The word is estimate or approximate or educated guess for the actual effect of the vaccine. Now, when you do this kind of experiment, depending on how you did the experiment, there is a possibility that, for example, suppose you are able to do this experiment several times. Suppose one person select a random sample and then he divides into two, and then he carries out this experiment. So he will have one estimate for the actual treatment effect, vaccine effect. So his estimate will be one value. If somebody else did the same experiment with different type of people but the same method, he will have a different value because his sample proportions difference between these two will not be the same. Right? So you can understand that this sample proportions are not going to be fixed values. It's going to be depending on the experiment to experiment. If we assume that we can repeat this experiment in different situations, we will get different estimates. Our estimates will be different. Right? So theoretically, sometimes we cannot find out actual value, but there, as I mentioned in the last class, there is always a difference between the actual effect and the estimated effect. Estimated effect is the value that we get. Actual effect is an unknown quantity. But there is a difference always. That difference is called the error in our estimate. Right? So error is not a fixed value. Error is going to be a variable, because in one experiment error will be one value. In another experiment, if you do the same experiment in a different situation, his estimate will be a different estimate, and therefore his error will be different. So generally, this error term can be positive or negative. Right? In one experiment, the error can be positive. In some, it can be negative. Right? So if you just think about, as I mentioned, you will not be able to find out this error. Right? Remember, I told you in the last class, we will never be able to find out the actual size of the error. Why? Error is equal to our estimate minus the actual effect. Estimated effect minus the actual effect. We know the estimated effect, but we never know the actual effect. Therefore, we never know the actual value of the error. But theoretically, we can show that in some situations, in some experiments, if you find out the average of these errors, right? If you repeat this experiment, you will get different errors. Some of them are going to be positive values, some of them are going to be negative values, some of them may be very small number of errors will be negatively large or positively large. Most of them, those errors are going to be close to zero, but negative or positive, but close to zero. Right? If that is the situation according to our design of experiment, then we say our estimate is coming from an unbiased estimate. Unbiased. Right? So estimate the error can be positive or negative. On average, the error is zero. On average, error is zero. If that is the case, then we say we have an unbiased estimate. Our method is unbiased. We are using an unbiased method. But suppose, for example, if you are using some method, some design, in that one also you assume that you can repeat this experiment, and suppose if we repeat, the error is always going to be either positive, always positive, or always negative. Right? If that is the situation according to your design, in that case we say our method is a biased method. Right? Error is always positive, or error is always negative, and therefore on average, error will be positive or error will be negative, not at the same time. Right? In one design, error may be positive, in another design, error may be negative on average. So that kind of designs are called biased. The reason we say result is biased and the design is biased, and so on. So therefore, what we look at in the bias is whether the error in our result, always there is a possibility of error. If the error on average equal to zero, then we say we have an unbiased situation, unbiased design, unbiased result, and so on. But if there is a possibility that if the error is positive always, or error is negative always, in that situations we say our results are biased and the experiment is biased, the design is biased, and so on. Now there are different ways this bias can occur. Right? One method is by something called confounding. Right? Some phenomenon called confounding. We will come to that. I actually explained in the last class, but I will explain again. So if there is a confounding in your design, right, some variables are confounded, some effects are confounded, because of that a bias can occur. And that kind of bias is called confounding bias, bias occurring due to confounding. And there are similar biases like other situations because of other reasons. But here, if the confounding bias occurs because of confounding, we call it the confounding bias. So what do you mean by confounding? Confounding is a situation where that happens. Suppose you are looking, you want to find out whether there is an effect of the treatment, right? Polio treatment, for example. So you are considering two variables in this case. One is because you have two groups of people. You can consider one variable considering whether the person is in the control group or whether the person is in the treatment. So therefore, we can say it's a group. Is the variable. Group is the variable. It can be defined, for example, group is equal to 0 if they are in the control group, 1 otherwise, or maybe 1 when they are in one group, 2 otherwise, like that. You can give some labels to that. But there is a variable group to which they are belonging. The other variable is the outcome. Outcome also in this case a binary outcome. In the previous variable also binary variable. It has only two possible categories, right? Treatment group and the control group. Outcome variable in this situation in polio experiment is whether the person get the polio or not. Right? So that is the outcome. So we want to find out whether there is an association. First of all, we want to find out whether there is an association between these two variables. What do you mean by association? So you have two groups, right? Treatment group and control group. So you have at the end, you have the result. You suppose you find out the proportion of people who get the polio is P1 here, and proportion of people is P2 here. So when do you say there is an association between the group and the outcome? You would say there is an association if what?
Higher outcome.
Yeah, higher or low. If there is a big difference, usually if the P1 and P2 are somewhat considerably different, then you would say this group is different from this group, and therefore there is an association. There is an association. So that's what you generally mean by association. Right? In the two groups, if the two results are different significantly, then usually we say there is an association. Right? But in this case, actually, not only that, we are interested in finding out whether there is a causation, whether actually the treatment is causing the cure of or not getting polio, right? Prevention of polio, right? So that's causing. So association and causation are two different things. I'll explain that with some examples in the second chapter also. So you have already two variables, but suppose now there is a third variable, some other variable, which is associated with this and this both. Right? Some other variable which is associated with the group variable, whether they are getting the treatment or not, and also this variable is also associated with the outcome. If there is that kind of variable, right, related to this experiment, then we say that kind of variable is confounding variable. Confounding variable. A third variable which is associated with both the status of the treatment, whether they get the treatment or not, and also the status of the output. So that kind of variable is called a confounding variable or a confounder. Confounder. Actually, there can be a confounding variable, but the effect, the effect of confounding variable can be removed or eliminated if you design your experiment in a proper way. Right? So we will look at some examples where there is a confounding effect, and there are sometimes how to remove that one by using the proper design of the experiment. So that's what a confounding variable is, so called a confounder. Right? And then, of course, in the experiments, which especially when you are using humans or animals, always we have to think about ethical considerations. For example, is it ethical to give the treatment to only a group, one group, and then give a placebo to other group? Because everybody would like to get the cure, right? To be cured if you separate from some illness. So in this kind of experiments, you usually have to give a placebo to some people. So in one way, it is an ethical problem. But on the other hand, these trials or experiments are done to find out whether a new drug is good or not, right? So there's a possibility that these have some bad side effects also. So giving this to everybody will be then detrimental in that case. Right? So in that case, leaving some people out will be also okay, right? So like that, you can argue in both ways. But of course, whenever you especially use the humans, before that usually you run the experiment with animals a large number of times with different doses and so on. And if there is only some hint that this experiment, this drug is effective, then you will go to do it with the humans. So, but there is always ethical considerations, right? So let's quickly recap about the SARS polio vaccine trial. Do you remember this experiment that we explained in the last class? So what was the situation? There was this SARS polio epidemic, and then this new vaccine came up. And then there were different proposals for designs to carry out to find out whether there is actually a real effect of this vaccine. So we discussed about two of them. Actually, those are the two designs that was carried out. One was carried out by one group. That is called NFIP design, National Foundation for Institute Planning. NFIP design. Now, remember I told you that this polio is prevalent more among children, right? Children in low grades, like grades 1 to 3 were the vulnerable group, right? And there were some known facts about this. That is one thing known was one thing is it is prevalent among children, and the other one is it is more prevalent among rich people than poor people. Right. So these were known facts. So when you so that means actually there are two possible confounders. So we are going to look at the relationship between this and that. There is a third variable. For example, the grade of the student. So grade is the same as the age, right? Grade 1 to 3 is very similar to age. So age, you can consider age. Age, this one is related to age. It is known that young people get more polio, the incidence rate is large than the older people. So age is a possible confounder. But it will be confounding, it will be actually a confounding variable. It is also associated with the group. Right? We know that the age is related to outcome, is already known. This will be a confounding variable if it is also associated with the group. Right? So depending on the design, sometimes it may be associated with the group, or we can probably make it that doesn't associate with the group. If that is possible, then confounding will not be there. Right? So this is in this NFIP experiment. Of course, the treatment can be given to children whose parents consent on, right? If the parents don't like, we can give the treatment. So that is another thing that we have to consider, right? Treatment can be given to the children whose parents will consent, and we know that. So income level, or there may be social class, is also possible confirmed because we know that outcome depends on that. Right? Rich people are more vulnerable, or the incidence rate is large among rich people. So this variable, for example, income level or maybe the social class, they are almost the same, is associated with that one. We already know. But that variable will become a confounding variable if it is related to the group also. Right? If it is not related to group, then it will not be a problem. Okay, so remembering these things in our mind, we have to consider this. There are two designs, so we will look at the two designs. In the first design, in the FIP design, what they did was they took all the children in grade 2, only those children whose parents give the consent in grade 2 were given the treatment. So that is the treatment. Children of those parents who give the consent, but in grade 2. And then grade 1 and 3 is considered as the control. Now, in this experiment, if you did like that, then let's see the variable age now. And we knew that age is associated with the outcome already. Now let's see whether age is associated with the group. That means group means whether they are getting the treatment or not. So now, what do you think? In this experiment, does the age is the age associated with the group? If you do that, yeah, it is. Why? You can explain it in different ways. For example, in the treatment group, all the children are in grade 2. Right? In the other one, completely 1 and 3. So these two groups are completely different with respect to the age or the class. So therefore, we say this variable is associated with this one, right? In one group, there is a high proportion, almost everybody, exclusively everybody is in grade 2. The other group all are out of grade 2, 1 and 3. So this is completely two different groups, age groups. So that means this variable is associated with this one. So in this experiment, therefore, if there is any effect in age, that will be confounding the real effect between these two. Right? The real effect will be confounded by the age unit. So that is one problem in this design. The other variable was the parents' consent, right? Parents' consent, or it is the same as it is equivalent to the social class, right? So, and of course, some people, poor people also will consent, but most of the people who will consent will be rich people. Right. So, let's consider that variable. Let's call it the parents' consent, for example. So, in the treatment group, everybody is a child of a person whose parents give consent. Everybody is, otherwise they cannot give the treatment. But in the control group, there are people who will be giving the consent, and there are people who will not be giving the consent. In other words, in the treatment group, most of the children are rich people's children. Of course, some poor people will also give consent. They give consent, but we know that most of the rich people give consent because they know already that they have a high vulnerability to get the polio, because therefore they want to remove the risk from their children. Therefore, they would like their children to get the vaccine. So therefore, high proportion of people with high income will be in the control group. The other group will be completely different. So that means that variable, whatever parents consent to, you can call it to the social status or the whatever, that similar variable is associated with this variable. Therefore, this variable also will be a confounding variable. Right. So when you have that kind of confounding variable individuals, one or two or more, a bias, the result can be biased. Result can be biased. So therefore, that kind of experiment is not a very good experiment. If you have some estimate for the effect, you definitely know that it's not an unbiased estimate. So it is either positively biased or it is negatively biased. So therefore, those are the weaknesses of that experiment mainly. Right? But that was done anyway by many people at that time. But later on, they recognized that there are these possible confounding. Right? The other experiment was what is called double-blind control randomized experiment. Now, in this experiment, there was no blinding or anything. Everybody knew who is getting the treatment, and everybody knew who is not getting the treatment. Right? So there's no blinding anyway. So in this experiment, first of all, of course, again, children have to be given the permission from the parent. So there is out of the population, first of all, there are two groups: those parents who will give the consent and parents who will not give the consent. So we have to now consider only those people who give the consent. Right? The treatment group and the control group both should come from this subset of people, right? We have to completely leave out those children whose parents don't give the consent, right? So we first of all have to consider children whose parents will give the consent, and then out of those select a sample of children randomly again, and then randomly divide that sample into two, right? Randomly divide that sample into two, and then randomly decide which of these two groups is going to get the treatment and which is going to get the placebo. In this case, they used a placebo. In the previous one, there was no placebo. Right? There was a control group, but there was no placebo. Right? So therefore, in the previous experiment, we can call it's not really a experiment in the sense. It's kind of an observational study in the sense, because one thing is that there is no control, right? Well, there was a certain amount of control, but there is no randomized control, right? All the people in the treatment group was group grade 2, the other one was 1 and 3. There was no randomization at all. But in this one, randomization was there, and blinding is also there, because the children didn't know whether they are getting the placebo. The placebo was also a vaccine, but it didn't have any effects like salt or something. And after some time, the doctors have to decide whether these children have polio symptoms or not. So the doctors also didn't know whether this person has got the real vaccine or the placebo. So therefore, it was a double-blind, controlled, randomized experiment. In this experiment, now let's see, still the possibility of age associated with the outcome and possibility of the concept, right? Associated with the outcome is still there. But now, let's see, age. Is age a confounding variable here? Why not?
It is not associated with the group.
Sorry?
It is not associated with the group.
How do you say it is not associated?
They randomized the group.
Yeah. So that means, in layman's, for example, if you look at the two groups, In the first group, there is all the ages, 1, 2, 3, all the ages are there, right? In the second group also 1, 2, 3, all the ages are there, all the classes are there, and they were randomly decided, right? Therefore, there is no particular high or low proportion of one grade. For example, we can say, okay, this group has more children in grade 1 and this one has the other children. It will not happen when you randomize. Right? So therefore, in this one, both groups are very similar with respect to age. Both groups are very similar with respect to age. So that means age is not associated with the group variable. If one group was one particular type of, for example, grade 2 or grade 1, the other ones are in grade 3 and so on. If in that case, there is an association. But these are not similar, right? Two groups are not similar with respect to age. But when you randomly select all the children out of grade 1 through 3, of course, only children whose parents in person. But in that subset, there are grade 1, grade 2, grade 3 all children. So when you divide them into groups randomly, two groups will be very similar, not exactly the same proportion, but it will be very similar with respect to age. And then if you look at now all these people have been given consent, these children have been given consent. So that means there can be a large proportion of, in the first sample that we are considering before dividing, right? In that sample, there may be a large proportion of people who are rich people, small proportion who are small, maybe the less income. But then we divide that sample into two randomly. For example, suppose there was 70% rich people and 30% low income people in the first sample that we consider, right? Out of children, out of those who give consent. But then we divide that into two randomly. So then it will be going approximately the same proportions, and therefore two groups will be similar with respect to, for example, income distribution. Income distribution will be different. In this one also maybe 70% and 30% roughly, and the other one also there may be 70% and 30% roughly, not exactly. So therefore, in that case, income variable is not associated with the group. So therefore, that variable is not a confounding variable in this experiment. In the previous one, it was a confounding variable. So like that, when you do this kind of randomization, of course, what happens is if there is any possible confounding variable, they become not confounding because they will be distributed evenly among the two groups, and therefore the association, the possible association will be broken, and therefore it doesn't become a confounding variable. So therefore, when there are no confounding variables, confounding biases are not there. Confounding bias is not there. So therefore, this is actually the best type of design. This is the usually called gold standard design for this kind of comparison style. Whenever possible, apply this design. There are situations where it is not possible to apply because of some practical reasons. But whenever possible, you should apply double-blind, controlled, randomized experiments if you want to compare two groups and find out whether there is an effect. And in this one, you can find out, you can estimate the effect correctly. That means unbiased estimate. Okay. So that explains most of the words that I wanted to explain, but I think I didn't talk about the placebo. So this was the result of that experiment. This is the double-blind, randomized, controlled experiment. The other one is the NFIP design. So in both you can see that the rate of occurrence, right, after the experiment, the doctors decide each person whether he has symptoms or not. Depending on that, we can find out the rate. Rate in this case given as a number of polio cases 100,000. So these 28 for 100,000, 78, 31 for 100,000, and 48 so 46. So that's calculated as the total number of cases divided by this number multiplied by 100,000. Right. So you can see that in this double-blind experiment, rate of polio in the treatment group was much lower than in the control group. Here also it was like that. In this design also, this is the treatment group, grade 2, what is got this. So 25 for 50, 25 for the treatment, the other one 54. So that is also a big difference. Now, if you didn't do this one, people might look at this one and just based on this thing, they will decide that there is a treatment effect. This thing is polio vaccine is effective. But even though these two now, this is much smaller than this one, in this kind of experiments, we cannot actually decide that the vaccine caused the reduction here. Right? Because there are two other variables which affects the outcome. Right? So we don't know in which way actually they affected. Right? It's possible that maybe they have done this reduction, not the treatment itself. We don't know because there was a confounding. The effects are mixed and we cannot separate them out or we cannot cancel them out. So therefore, even though this number is more than this, statistically we cannot decide that the polio vaccine was the reason, polio vaccine for the cause for the reduction. In this case, causation cannot be implied, it's not implied. But in this experiment, of course, if there was any variable which will affect the outcome, that was only the treatment, all the other ones are similar, all the other age was similar in the two groups. Income level was similar, right? So those are the variables that we think that affect the outcome. So those variables are very similar in the two groups. Therefore, if there is any difference, that is the treatment. So therefore, this difference must have occurred due to the treatment, and therefore we can get the estimate and we can call it really the treatment effect. Okay. So we have discussed the weaknesses and so on. So I have actually changed a little bit of my note. Previous note there were some errors also. So here I have drawn a graph to show you what a confounding variable is. Right? So we are looking at the relationship between these two, but if there is a third variable which is associated with both of these, this variable is called a confounding variable. And those are the two main requirements, and there is a third requirement actually for a variable to be a confounding variable. So these are the three requirements for a variable to be called a confounding variable or a confounder. Right? So that variable should be associated with the treatment status, that is one requirement. It must be associated with the outcome also. Right? So this must be associated with both variables. And in addition to that, it should not be something called intermediate variable. If it is an intermediate variable, then we don't call it a confounding variable. So the difference between these two can be shown using a graph or a diagram like this. In this situation, we are looking at the relationship between these two variables, treatment status and outcome. So there is a third variable. This variable is associated with this one. This variable is associated with this one. The similar situation can occur like this. We are looking at the relationship between these two variables. There is this third variable is in the middle. Right? In that case, we don't call it a confounding variable. We call it the mediating variable. For example, now you are considering the status of the treatment, whether the person got the treatment or not, outcome, whether the person got the polio or not. Suppose the third variable we consider whether the person has improved his immunity or not, whether the immunity was improved or not. let's consider that variable. Right? So that variable is going to be in the middle, right? If treatment improves the immunity, that improvement of immunity will prevent person getting polio. Right? So in that case, it's not a confounding variable; it's called intermediate variable. Right? So the problem occurs actually if you have this kind of situation. The problem doesn't occur because of this kind of variable. So that's the difference between a confounding variable and an intermediate or mediating variable. Okay, so in this one we have discussed this part. And then I want to, in this situation, therefore, in the NFIP design, read the situation. Right? So we are interested in the relationship between vaccination status and polio, but there are two other variables, age and patient consent, for example. So this one is confounded because this is related with this one and this one. So there is an association between this and that, and also this one is also a confounding variable because there is an association, and that's what we discussed earlier. So in the previous note, the graph was a little bit wrong. Actually, I had wrongly put an arrow here also. So that's about the confounding. I have just added some mathematical equation, but this is not exactly a modeling or something. I don't think that part is necessary, but if necessary, you can look at it in your note. It shows how the age effect and parents' consent effect cancels out in the second design, that is a double-blind, controlled, randomized experiment. When you look at the difference between the ratio of incidence ratio, if there is any effect, that effect cancels out. Right? So I can show it. I have shown it in mathematics here. So look at that. In the other design, it doesn't cancel out. Right? So when you look at the difference between the ratios, it includes the effect plus something. Right? So the effect is confounded with something else. We cannot separate them out, or we cannot eliminate the other part. So therefore, we don't get the real effect. So because you are mathematics students, I think you can understand this. Please go through it. If you have any question, please tell me next time. I will explain that. So we discussed this question in the last class. Therefore, I'm not going to do it again. So here I have actually modified my note a little bit to explain about the placebo effect. A little bit about the placebo effect. So the placebo effect in an experiment is a person's health condition that arises from the belief or expectation of having received an effective treatment. So when the person thinks that he has got a treatment, he doesn't know whether it is a placebo or the real treatment. Just because of the belief that he got a treatment, sometimes there can be some improvement in his health condition. Right? So if such an improvement is possible, that due to some effect, that effect is called the placebo effect. So it's just a psychological effect, not the real physiological effect. It's a psychological effect. Right? So I have mentioned that it is not the effect of the placebo itself, which is inert and so no active therapeutic value, but the effect of believing in the experiment. So there can be situations where this placebo effect is considerably large and really affecting the outcome, and there can be situations where it is not that important. So we can ignore that. Even if there is a placebo effect, we may be able to ignore that because that will not really causing a problem in our decisions. So here I have divided them into three parts. For example, in our experiment, if the outcome is completely subjective, right? For example, suppose we give two medicines. One, for example, there's a new medicine for say painkiller. So you want to find out whether this new medicine is a good one. So you are given a placebo also. So there are two groups. Suppose you consider randomized, double-blind, all these factors are there. But because the patients don't know whether they are getting the real treatment and the other one is placebo, there might be some effect. Right? Especially when in this kind of situation, the patient will say whether he got the relief or not. Right? For example, headache, usually a doctor cannot decide whether the person has a headache or not. Right? If it's about a headache, the patient has to say, I got a relief or not. So therefore, the outcome is subjective. In this kind of situation where the outcome is subjective, the patient says whether he gets a relief or not. In that kind of situation, this placebo effect can be considerable sometimes. Right? Because just because they think that they have got this one, sometimes people report that they have got relief, but that is not really a real effect. So therefore, in that kind of situations, placebo effect can be important. On the other hand, there are some situations where the patient feels something, but at the same time, doctors also can decide to a certain extent whether there is actually a real improvement. For example, suppose there is some medicine for anxiety, for example, right? Anxiety. So when you when the patient gets this treatment, he can say that one way that he can say that he gets some relief, right? On the other hand, this anxiety reduction or increasement of anxiety might change some other thing also, like blood pressure and so on. Right. So in an indirect way, for example, doctors also can see whether there is some change. Right. So if doctors also can intervene, sometimes the effect made by the patient's report may not be that important. Right. Doctors also know, so therefore we can actually make some adjustments to these results and so on. So therefore it may not be that important. The third type is actually directly doctors can decide whether there is an effect or not. For example, in the polio case, people cannot say whether they got polio or not usually. The doctors can definitely say whether he has polio symptom or not, because the doctors know what are the symptoms and so on. So in that kind of situation, actually, this placebo effect will not be that important. Placebo effect will be there, might be there. For example, in the NFIP design, when people know that second grade students there, they know that they have, they get the treatment. One thing is that they might, for example, because of that, I don't know, their immunity might be increased and therefore maybe can be reduced. So if that happens, if that is possible, then we can call the placebo effect. Immunity, because of not actually, you cannot even call it that, not placebo effect, right? So actually in that kind of situation, I think placebo effect cannot occur, because placebo effect is the effect, psychological effect that gives the improvement, right? So when you get, but there can be something like this. For example, when people get the treatment, they think that, okay, we are now less vulnerable to the polio, and therefore we can, for example, go everywhere very freely and so on. So therefore now, indirectly they may be exposed to the polio to a high level, but that is not the placebo effect, that is something else. Right? Placebo effect is the effect that is occurring psychologically and giving the improvement. But in this case, actually, for example, polio case, placebo effect is almost no effect, or if there is any effect, that will be negligible. So in the NFIP design, if there is any maybe there is some kind of psychological effect possible, I don't know, I'm not a doctor or anything to explain, but if there is any, that will be very small, so we don't have to worry about that effect in this experiment. On the other hand, in the completely randomized design, even if there is a placebo effect will be the same in both groups, because these people don't know whether they are getting the treatment. People think that they are getting the treatment. Placebo people also think that they are getting the treatment. So if there is any possibility of getting psychological improvement, both group people get the same improvement. Right? So therefore, when you take the difference between the ratios, this improvement effect will be cancelling out. Right? So therefore, even if there is a placebo effect, even if the placebo effect is very significant, still that will not be a problem in the randomized design. So that's what the placebo effect is. So usually you have to be careful about the placebo effect, especially if the outcome is mentioned, outcome is reported by the patients. If it is subjective. Right. So this is an example where the placebo effect was actually very significant. It is called gastric freezing experiment. Right. So in this experiment, some treatment called the gastric freezing was recommended for something called peptic ulcers. I think peptic ulcers are the ulcers, I don't know really, but I think it is in the stomach. So in this case, the proposed method was to insert a tube filled with very cold liquid into the patient's stomach. With the idea that cooling would reduce acid secretion and allow the ulcer to reheal. Right. So this was the proposed method, to insert some cooled liquid into the stomach so that the content of the stomach will be frozen to a certain extent, and that will reduce the secretion of acid into the stomach, and that will heal, that will give some time to heal for this ulcer. So at the beginning, some people were doing some experiment. That means they just do this experiment do this procedure to some patients. It's not really an experimental setting, but they do these things to some patients, apply this to some patients, and most of the patients were reporting that they get some relief out of those who underwent this treatment. Most of the people were reporting that they got some relief. Right? In that case, actually, that was a subjective outcome. Patient was saying whether they got relief or not. Right? They were not using any other thing to check whether really the ulcer was healed or not. So they were not using any ultrasound or X-rays or anything. Patients were telling whether they got relief or not. So according to that, doctors were saying that okay, most out of the patients who got this treatment, most people are saying they got relief. But then later on, some person did the controlled experiment, randomized controlled experiment. In that one, they use a placebo method. Right? So that means in that case, they also injected a certain other thing, but it is not actually freezing the thing, but these patients were not aware of what this was in, and therefore it was some other similar method, but actually it is not doing the same thing that the previous treatment was doing. Right? So in that experiment, they really they saw that when they look at the values, they saw that actually there is no real effect of the treatment method. This gastric freezing method doesn't have a real effect. That means the ratio or the difference between the proportions of people who got the relief were roughly the same, right? So then, why did people were saying that they got the relief? Because of the placebo effect, actually. So actually, the treatment doesn't have any effect. In the placebo group and the other group, finally when they did the randomized experiment, they found out the proportion of people who got the relief were roughly the same. So that means there is no real difference between these two methods. But there was some improvement. There was some improvement in both groups. When they did the randomized experiment also, there was some proportion of people who were saying they got relief. The other one also they were saying they are. So how did that relief occur? Because of the psychological problem, psychological effect. That's the placebo effect. So that is an example where the placebo effect can be significantly large, and therefore people might wrongly decide that that is actually the real effect of the treatment if a randomized experiment is not carried out. Okay, shall we take a small break?
Without any controls or control. So this is called portal shunt study. This was a surgical procedure for cirrhosis. So early uncontrolled reports. Right? So this procedure was applied for patients. So early uncontrolled, what they were really interested in was actually to see whether whether these people who undergo this treatment live longer than there's a usual treatment, is a new treatment, right? So they wanted to find out whether these people undergo this treatment, new treatment, live longer than the other people. That was the objective of the experiment. So early uncontrolled reports showed that suggested procedure was beneficial. So this surgical procedure was done to some patients, but there were no control group, so they showed some improvements. Right? So, but later on, some persons did some controlled experiments, randomized controlled experiments. In that one, when we look at the difference between the survival rates, so survival length of survival, they saw that there is no real benefit from this experiment. So real benefit from the surgery. So the previous one didn't involve surgery, this one involved surgery, so actually there is no real benefit. Doing a surgery is very expensive and maybe it is very dangerous also. Actually that's what they found out when they did the real experiment with the controlling randomization and so on. They found out actually this procedure is not helping, not improving, but it may actually reduce the survival time also. Right? It goes the other way around. Right? So what was happening there? This was the data. So there were some experiments earlier with no control at all. So these are the these are the actual numbers, not the proportions. So out of 24 and 33 no control experiments for surgeries, 25 had marked improvement and 7 had moderate improvement and only 1 had no improvement. And then there was some experiment with controls, that means they compared with some patients who didn't do the experiment, who didn't undergo this new treatment, but it was not randomized, of course. Like people were not divided randomly into 2 groups and then did the surgery on some people and not. It's not like that. There were some people who underwent, but then they compared with some other group. In that one, they saw that 10 cases with marked improvement and 7 with moderate improvement and 2 with no improvement. But when they did some few experiments with randomized controlled experiments, they didn't see any marked improvement cases. There was 1 moderate improvement and 3 no improvement cases. So, based on this one, they decided that actually this procedure, the new procedure, is not worth doing because it's an operation and it doesn't really improve the survival time of the patients. And actually, sometimes they saw that it is even reduced. Right? So, how did the earlier patients saw that there was an improvement? There was some kind of bias in the way that the experiment was done. So, there are patients who are eligible for this kind of experiment. We cannot do operations on everybody, right? For example, nowadays, I remember when somebody was doing that, Mr. Ranil needs some operations. There are some blocks, but probably doing operation is not good because he is old and so on, right? So age is a matter. Some people, right? Maybe for young people that people will do an operation quickly, but for him, an operation may not be that good, right? So therefore, even if there are patients, some patients are not eligible for this kind of treatment, right? So there are two groups of people who are eligible and not eligible. Right? So in a controlled experiment, of course, they will consider first of all they will take only eligible people, like in the start vaccine. They take only the children whose parents give consent, only that group, and their group is divided into two. And so here only eligible patients are divided into group in the controlled experiments, and then randomly divide them into two, and then one group randomly selected for the surgery and the other group selected for the control. So that is the real experiment. But what they were doing earlier was they didn't do. Now there may be some group of people out of this eligible also. There are people who are somewhat more severe and less severe. Right? So they were doing the operation only on less severe people in this group. All the other severe people were not considered. Right? So because at the beginning of the experiment, of course they were not very severe. So when they did the experiment, anyway, whether the surgery was good or not, they were still living for a long time because at the beginning they were not severe patients. Right? So that was the reason. Right? They were not comparing with the other people. So somewhat severe people, they were not comparing with somewhat severe people. Right? In this one, this group has both severe and non-severe people. This also has severe and non-severe people. Therefore, you can compare. But here, only non-severe people were done the surgery. Right? It was done only on these people. Therefore, at the beginning, even before the surgery, they were still going to live for a long time anyway. Right? So therefore, after the surgery, they think that they live long because of the surgery. So that was the reason. Right? So therefore, that again shows the importance of doing a randomized controlled experiment whenever possible. So in this case, you can see that there are randomized controlled experiments and randomized controlled but not randomized. Right. So this is there is some kind of control here because there are two groups and they are doing this thing only for these people. So that is a control because they decide who is going to be operated on, right? So, but it is not randomized. Okay, so that is that. And then finally, as I mentioned earlier, it's not always easy to do randomized controlled experiments. Right? In a randomized controlled experiment, what is the most important thing? You have to have the two groups who are getting the treatment and not getting the treatment, and these two groups should be very similar in all the possible ways, except whether they are getting the treatment or not. So if there is any possible confounders, then those possible confounders where it should be similar in both groups. Right? But getting this kind of situations, this kind of two groups is not easy always. Right? So therefore, sometimes what people do is just do some experiment and then compare your result with some previous historical results. That is not a good way to do it, because we don't know whether in the history, in the historical experiment, whether they had a similar group of people or not, we don't know. Right? So even though people compare new results with the historical results, it is not a good way of comparing, and therefore sometimes you have to be very careful when you are interpreting that kind of results. So that's something you explain in the book, so I included that part also. Okay, so I think that ends this section. So this is a situation where the previous problem, right? Operations were done only on the healthier people, right? They were, of course, they were sick, but they were relatively healthy. So they were telling, okay, some people, but I don't need the experiment because I don't need a surgery, but people of some kind of forced to do a surgery, even though they didn't require. So therefore, finally they saw that they were living anyway for a long time. So the long lifetime was attributed wrongly to the effect of the surgery. Okay, now we will go to the next section where we discuss about observational studies. Here I have changed the order, because in the book, not here actually, in the next section I have changed the order. Here also I have changed the order. No. In the next section they talk about histogram and so on. I changed the order in the material. Okay, so let's look at this. So observational study is different from a control experiment in the sense that who is going to get the treatment and who is going to get the control is controlled by the researcher in the experimental study. Here it is not like that. Right? So this kind of experiments usually occur in social science settings. Right? Not even in scientific settings is possible, but in most situations, social science settings where we cannot control like that. For example, suppose you want to find out whether there is an association between smoking and lung cancer. So we cannot get two groups and then divide into two groups and ask one group to smoke and the other group not to smoke and follow them up for a long time and see how many people or what proportion of people got lung cancer. That's not possible at all. So there are situations where we want to find out whether there is some kind of relationship between variables, but it's not possible to carry out experimental studies. But still we want to find out whether there is some kind of relationship or association. Right? So one important thing here is actually, if you want to establish a causation, right? Whether one variable is causing the changes in the other variable, this kind of experiments will not help you. If you want to establish a causation, the best method is actually experimental studies. They are also randomized, controlled, if possible double-blind experiment. But it's not always possible. In observational studies, even though you cannot actually decide whether one variable is really causing the changes in the other variable, if you do it properly and in a proper way, then still you can get some idea whether there is a possible causation. It will not be a proof, but there will be some indication that there is a high possibility that there is an association. Right? So that is important. So we will discuss about that kind of situations here. Right. So I have given you some examples of observational studies in different fields. For example, researchers track a group of smokers and non-smokers over 20 years to observe the incidence of lung cancer. So they do not assign them randomly to two groups. Just observe how they are already Right? So, but we want to find out whether there is an association. So, this word is important, association, right, between smoking and lung cancer. We are not, in this case, we cannot find out whether the lung cancer is caused by the smoke, but we can find out whether there is an association. And then in education sector, the study records students' attendance and their final exams in university scores. The researchers do not control attendance. You cannot say, okay, you come to class and you don't come to class, and we'll see the final, we'll see what happens in the final exam, right? So that's also not possible. But they want to find out whether there is a relationship, some kind of association between attendance and final marks. In the health sector, health officials analyze dietary habits and body mass index reports collected through national health surveys without assigning, so they are also no control. We want to find out whether the existing relationship between eating habits and obesity. So like that, there are a lot of situations where we want to establish or find out whether there is an association. Relationship first of all, and then association, and then causation. There are actually three words that is used here mainly. I have just mentioned about these words. Relationship is a more general term. Relationship can be a statistical kind of relationship, or even it can be a mathematical relationship. For example, we know a lot of mathematical equations, say final velocity is equal to initial velocity plus acceleration times time v plus v is equal to u plus v ft or something. That's a mathematical relationship. Statistical relationships are there, and then also social relationships, friends, right, enemies or whatever. So that's also. So therefore, the word relationship is a general word. But when you want to talk about statistical relationships, usually we use the word association. Association is a statistical relationship usually. Right. And then a particular type of association is a causation. Right. So it's a more strong association. Causation means when you change one variable, because of that, the other variable will change. If you stop changing that, the other variable will stop changing. So that's the causation, directly influences. So therefore, you can show that the relationship is actually a general one, and part of that is association. So there can be only association without causation, or also there can be causation situations. The important thing to understand is, if you want to establish a causation, best thing to do is an experimental study, if possible. Otherwise, if you are using an observational study, you cannot actually establish a causation. Really, you cannot prove a causation, because there are always confounding variables. Some we know, some we don't know. Right? Because in this kind of studies, there are so many other variables affecting the relationship between the two variables that we want to look at. Right? So some maybe we know that there can be some effect, maybe there are other variables which we don't know, but still causing some effect on the relationship between the two variables. So therefore, it is not always possible to identify all the confounding variables. Right? There can be some known confounding variables as well as some unknown confounding variables. If there are only known confounding variables, it is sometimes possible, when you are using an observational study also, it's possible to do something called control for those non-confounding variables. Right? So we carry out the experiment and then do some kind of analysis. In the analysis, right, not in the data collection, in the analysis we can use something called controlling for confounding variables. Right? One method is called the regression analysis. In the regression analysis, we include all the variables into the model, and by that we control for those confounding variables, and therefore find out the effect of the interested variable. Right? So that kind of thing is possible sometimes if you know the confounding variables. Right? But if there are other confounding variables unknown to us, that method will not work. Okay. So I have given here a few examples for only causal, associations, and that means non-causal associations and causal associations. For example, one might say people who drink more coffee are more productive. So can we say that coffee is making people productive? If that is possible, then it will be a causation, causal association. But if there is some association, that means those who drink coffee are more productive, but those who do not drink coffee are little less productive, that will say that there is some association, but it may not be a causation. Right? So in that case, there may be a third one variable or several variables which are affected by coffee, for example. So coffee affects something and that variable affects the productivity. So coffee doesn't directly change the productivity, it goes through some other variable. In that case, it's not a causal relationship. It's not a causal relationship. Right. So, for example, households with washing machines tend to have longer life expectancy. So if households give you long life, everybody will buy washing machines, right? That will not make your life expectancy long, right? But there is a belief like this. How can that happen? How can you explain that? If there is an association like this, how can you explain? Right? People have found out there is an association like this. Yeah, that's right. So there is a third variable definitely, right? So those are when we have washing machines and they also have good life, for example, they have good food, good medical care and everything, right? So therefore that leads to long lifetime. So therefore washing machine is not causing their life to be long, but some other reasons which is also related to these two. So therefore it's not non-causal, but there is an association. Children with bigger shoe sizes tend to have better reading ability. How can that happen? Bigger shoe sizes have better reading ability.
So we must have good nutrition, so we must have money or something.
Nutrition. Yeah, that's one possible explanation. So you mean when you have good nutrition, your food becomes large?
Yeah.
Yeah. That we cannot say no, it might be a possible explanation, but there are any other explanations for this? There can be, for example, age is related to this, right? When the child becomes large, of course, food becomes large. At the same time, he becomes more able to read. So there may be age, time, right? Time factor associated with both variables, and that would show like this one is age, right? Exercise reduces the risk of blood pressure. So there is, for example, if you collect data of those people who exercise and their blood pressure, you will see that there is an association. Those who do exercise have low blood pressure. So those who don't do that have high blood pressure in general. Right? So that's what you mean by association. Two groups have two different values for the outcome, and that means that there is an association. But can that be a causation? It's a problem. Right? So in this case, of course, we can test it using a randomized experiment. Right? If you want, you can test it using an experiment, and people have done that actually. And then they have actually found out that exercise, usually they say exercise reduce blood pressure. That's how they write it, right? They say usually exercise reduce blood pressure, but that is not exactly correct because all the people who exercise don't get reduced blood pressure. Right? What happens is actually high proportion of people who exercise get reduced blood pressure. Right? So that means the risk of high blood pressure is decreased by increasing exercise. So that's the meaning of it, but that can be actually a causation. We can prove it is a causation by doing a randomized experiment also. And similarly, smoking increases the risk of lung cancer. Now, in this one, actually, we cannot do a controlled experiment, right? Smoking case, we cannot do a controlled experiment. Even so, with even observational study, people have actually now decided that smoking increases the risk of lung cancer. Right? We'll talk about how to decide the causation using an observational studies little later. Usually people look at several criteria to decide. We are using an observational study. Usually you cannot decide directly, you cannot decide causation based on that kind of observational studies. But if you check several criteria with that and if most of the criteria are okay or satisfied, then even from the observational studies, it's possible to decide the causation, decide that it's actually causation. So we talk about now this one, in a multiple choice exam, number of errors reduced when the number of corrects. Right? Number of errors reduce number of corrects. When the number of corrects increase, number of wrongs goes down. What kind of is that association or what? It's not really an association, it's not a statistical. There's a relationship. For example, if you have 10 multiple choice questions, if you have 6 corrects, that means you have 4 wrongs. Right? So therefore number of wrongs and number of corrects is equal to 10 always, right? So that's a mathematical relationship. It's not a statistical association. In that kind of sense, we say it's a mathematical relationship. We don't call it an association. But some might say it's a causation also, because when you reduce that, the other one automatically increase definitely, right? So in that sense, some might say it's a causation also. But this is not a real good word to mention in this case because it's not a statistical relationship. Okay. Similarly, the number of free hours decreases the number of working hours, right? So because the total number of hours is 24, if you are working certain number of hours, the other number of hours is not working. Right? So therefore, when one is increasing, the other one decreases, the total is equal to 1. So one might say it's a causation, but really it's a mathematical relationship. Right. So the key point in this section is all causal relations, they are associations. Right? All the causal relationships are associations, except these last two. Usually we don't consider them as statistical ones. But not all associations are causal relationships. We saw in the previous situation. So establishing whether an association is a causation in observational studies is not as straightforward as in experimental studies. In the experimental studies, if you carry out a completely randomized controlled experiment, you can establish a causation because all the other factors are similar in the two groups. Only the treatment is different, and therefore, if there is any difference, the difference must be due to the treatment, and therefore, that is a causation. But in these experiments, there are so many confounding factors, known and unknown. Therefore, it's very difficult to establish a causation. So, in experiments, researcher can control exposure and randomize participants, which help rule out the confounding. In observational studies, however, researchers only observe what happens naturally, so causality must be inferred with caution. Right? If you are going to infer causation, if you are going to decide that this is a causation, you have to be careful. Usually, in observational studies, when people report their findings, they have to be very careful to write it correctly, otherwise the implication will be meaningless. Right. So what are the criteria that usually people look at, or we should look at to decide whether some association is found in an observational study, to decide whether that association can be a causation or not. Right? Still, it doesn't 100% prove, but maybe it's 95% sure it's a causation after checking several conditions. Right? So one thing is that you have to check whether there are confounding factors. If there's a confounding factor, or one or more, then usually it's difficult to decide the association is a causation. Right? Association may have occurred due to the confounding factors. So in that case, confounding factors, there is a way that you have to control for the confounding in the analysis. In that case, probably is possible, but most of the situations when they are confounding, it's not possible to control also, and therefore most of the observational studies do not help us to decide causation. And then time effect. If one is causing the other one, if X is causing Y, X must occur first. Y should occur later. Right? If X is causing Y, Y cannot occur first, no, before. Right? So therefore, time effect also. Right? So check whether if you want to decide Y is caused by X, and you see that X and Y are associated, you want to decide whether actually Y is caused by X. So then check whether X is occurring first, and then Y is occurring second. So that is only one criteria. And then strength of association. Usually there are methods to numerically measure the strength of the association. Usually we can talk about, for example, weak association, moderate association, strong association, and so on, based on some numerical measure. Right? So if the association is a causation, usually it's a strong association. If it's a real causation, association cannot be a weak association. So that is another criteria that we can look at, right? Whether the association is a strong association. And then consistency. If Y is caused by X, it cannot happen in only one experiment, or maybe 2 experiments out of 10 experiments, for example. Right? If Y is caused by X, it should happen always in every situation. Right? So that's what you mean by consistency. Right? So if the association is observed in different populations and different times and different study designs, you see the same association, same type of association, that may indicate it is actually a causation. Otherwise, if it is occurring in some situations and not occurring in other situations, it cannot be a causation. And then better if you can have some biological or some other theoretical explanation for that also, right? You should have a justification, right? Why this can happen. So that will strengthen our justification. And then dose-response relationship. Right? If Y is caused by X, is really caused by X, if you increase X, Y should also proportionately increase or decrease. So when you change it by a certain amount, proportionality it should change, Y also should change. Right? If there is only an association, we don't expect that kind of relationship. But if it is a causation, dose-response relationship should be there. And then reversibility, that means if you stop, for example, changing X, then changes in Y also should be stopped. Right? Because if it is causing that, then when you stop one thing, the other one should also stop. So these are several criteria, not only one. You have to check all these things in an observational study, right? Yeah, some may be not relevant, but you have to check all the relevant criteria to decide whether an observed association can be considered as a causation. And then finally, of course, coherence with the existing knowledge. So if you have some knowledge already, the new knowledge should be supporting that, not neglecting that or going against that. So if that is another reason, was to decide whether an observation is a causation. So let's see, now earlier we said that smoking causes cancer. People have already decided that. So when you say smoking causes cancer, that again, it doesn't mean that everybody who smokes get cancer. Right? So what it really means is that the risk of cancer increases when you smoke. That's what it really means. But when the people say smoking causes cancer. Right? Otherwise, if you talk about risk, people won't worry about that. Right? If you say smoking causes cancer, it gets into the minds of the people. So that's why definition is like that. So how was it decided? So first of all, in observational studies, they observed that those who smoke more are more likely to get lung cancer. That was one reason. Right? So in the observational studies, so they had some cohort studies, right? So this is again observational type, but they did it carefully. They observed a group of doctors in this case. Group of doctors who some of them were smoking, some of them were not smoking. Right? So they are kind of a specialized type of people. Right? So in this one, they saw that there is a clear, first of all, clear association. There was a high proportion of lung cancer among those who continuously smoked, and then less proportion in the other group. And there was also a dose response, one requirement. Dose response observation, that means those who smoke large number of cigarettes per day had high proportion of lung cancer. Right? So that's what you mean by dose response in this case. Right? When you are exposed to high amount of exposure, then the result becomes high, or maybe go the other way around if it is reciprocal. But in this case, they observe that. Temporarily, of course, they are, because lung cancer comes a little later. You are initially smoking, so that time-wise it is correct. So in addition to that, there were some case control studies also. So with lung cancer patients compared with mesh controls, right? So this is kind of again an observational study, right? In this smoking situation, it's impossible to do experimental study. Right? But in this case, this is somewhat between observational and experimental, because in this case, how they did was, for each person who is smoking, you choose another person who is not smoking, but with almost the same characteristic, maybe age-wise, gender-wise. You observe another person also, right? So each person is matched with the same characteristic, except smoking or not smoking, right? So this is called kind of a pair-wise comparison, matched pairs, right? So from that kind of experiment, it's possible to sometimes decide the causation, right? Because it's like almost like a controlled experiment. Right? Even though it's observed, people are not randomly divided into two groups, but for each person in this group, there is a similar person in the other group, almost similar, not exactly, almost similar with respect to mainly the possible confounders. Confounders, possible confounders, as far as the possible confounders are concerned, they must be matched. So that's a match control. Right? So from that kind of experiments also, they found out, from that kind of studies, not experiments, they found out there is an association. So all these things, from using all these things, now people have actually established or decided that actually smoking increases the risk of lung cancer. So conclusion, no single study could prove causation. You cannot prove actually, even still it is not a proof. But the body of evidence combined with biological understanding goes overwhelming. So therefore, now they have decided to report it like this. Cigarette smoking is a cause of lung cancer in men and probable cause in women also. So they have already seen that it is more true for men than women. But this might change a little later. For the moment, that's what we are observing. So today the consensus is clear. Smoking causes lung cancer and many other diseases. So they have decided on the causation, even though it's not a real proof. Right. Evidence is overwhelming. Right. Okay. So now let us look at this example. This is an observational study. So we are trying to understand how the design of the experiment or design of the study even affects the outcomes. Right. So between 1955 and 1958, families in Baltimore were displaced by slum clearance program. So like in Sri Lanka, they also had slums. They wanted to clear them. So some of these families were moved into, the government built some houses and they moved into those houses. Some of the people moved into their own new houses. Right. Some of these families moved into newly built public housing projects while others relocated to private housing. Researchers conducted a study to investigate how well families were adjusting in their new homes. In particular, they wanted to find out, the main objective of the study was to compare the adjustment of families relocated to public housing with that of families relocated to private housing. In particular, the researchers wanted to see whether families in one group experience more problems than those in the other. So the main focus was to find out the problems that they face, whether the amount of problem they face is different in the two groups. Some group went into public housing, the other ones private housing. So these are the data they saw. The data collected in this study are summarized in the following table. So there were altogether 190 families moved into public housing. Out of those 190, 80 reported problems, 110 reported no problems. And there were 240 moved into private housing. Out of those, only 30 reported problems and 210 reported no problems. So what can you say if you just look at these things and what did you decide? So out of this, if you consider the proportion, for example, right, the proportion of problems reporting is 80 divided by 190 for the public housing. This is 30 divided by 240. Right? So when you calculate these two numbers, definitely this number will be large. This number is large. So these numbers are there, right? So 42% families in public housing reported problems, and then only 12% of families in private housing reported problems. So at the first glance, it seems that those who went into public housing have a lot of problems. More families have problems. So is it correct to report it like that? Problems occur because of the housing type. Right? Problems, the amount of problem that people face is associated with the type of house. So when you are reporting these numbers and coming to the conclusion, you have to be careful. Right? What are the possibilities here? Is there any confounding factors possible?
Income level.
Sorry?
Income level.
Yeah, how would income level be associated?
So those who got into public housing, they must have low income.
That's right. Actually, that's what happened. Most of the people who went into public houses were little less income people. And rich people, of course, most of the people, I think almost all, but their own houses. So to begin with, those people who went into public housing had a lot of problems because of their income and so on. So even before they moved into that houses, they also had the problems, right? So the same problem persisted because their income didn't change, even though they went into new houses. So therefore, the houses is not the one really associated with the problems, the income. Right? So therefore, if somebody reports that housing is associated with the income, it's not really a good way to explain that, right? There is a confounding variable. Of course, really wrong to say causation. If you say, okay, the housing is the cause for the problem, that's going to be completely wrong, right? That will not be at all correct, but still association is also a problem. So the Baltimore housing study was an observational study, therefore we cannot decide the causation at all unless you have really good reasons, like most of the criteria are satisfied and so on. But families who end up in public housing were generally poorer than the other people to begin with. Right? So those pre-existing problems were actually continuing even after they went into the housing. So that's why their problem rates are higher. Right? So the observed association actually, there's association observed here, but that is not because of there's a real association, that's kind of a spurious association. Spurious association. That is caused by some other problem. So that kind of associations are called spurious associations. There are some other well-known examples also. For example, there was a data set somebody had collected number of children born in different months of a certain area. And somebody else had collected number of some certain kind of migrating birds coming into that area. Right? So every month you have two numbers, number of children born in that month, number of birds came into that area. So they plotted these things X and Y. So they saw that when the number of birds coming into the area increasing, number of children also increased. So there is an association, apparent association, but nobody can say that this is a real association. That's a kind of a spurious association, right? So maybe we are able to explain that, maybe we are not able to, but there is definitely it is not because the birds didn't bring the children. So there is a real spurious association. Similarly, there was these are real ones. The amount of ice cream sales in different months they had reported, and there are also some reports number of drowning in that area in swimming pools, number of drownings. So when the amount of ice cream increases, number of drowning also increases. So there is an association. So this is summertime when the temperature was definitely a third factor. Right? When the temperature goes up, ice cream sales goes up, and also because of that many people go for swimming, so many people drown, right? So that's a kind of a spurious association. Okay. Now let us look at another example where people have done a real randomized controlled experiment, but using that one they are trying to compare two things, and that comparison is not valid. So this is a coronary drug project, was a randomized controlled double-blind experiment. So this is a very good experiment designed to evaluate 5 drugs for the prevention of heart attacks in men with existing heart disease. So they were not actually testing one drug, they were all together considering 5 drugs, but in this particular example we are considering only one of those drugs. One of the drugs tested was something like called rate. Okay. Some name known to lower blood cholesterol. So that already known to lower the blood cholesterol. So the objective of this particular study was to test whether this particular medicine reduced the mortality among heart patients over 5-year period. So it was not the objective was not to see whether the blood cholesterol goes down or not. It was already established. Right? It was for blood cholesterol, but in addition to that, they wanted to find out whether those who get this particular drug get low mortality rate within 5 years. Right? So they did an experiment. There were 8,300 middle-aged men with heart problems. So they randomized this into 2 groups. Actually 6 groups they divided. So there were 5 different treatments. And then the 6th one was the control one. But here we are considering only one of those treatment groups who got this particular treatment, the others got the other treatments. And then there is a control. Right? So one group got this particular treatment for cholesterol, and there is a control group who didn't get any. Right? So using this test, they saw that actually finally they decided that this particular drug didn't improve reduce the mortality rate within 5 years. There was no effect of this particular drug on the mortality. Right? It reduces cholesterol, but it didn't actually reduce the mortality. So that was the finding. Right? So data analysis, overall mortality in this particular medicine group was 20%. Overall mortality in control group was just very close to that, 21%. So even though this was just 1 point below, it's not good enough. Strong evidence for us to decide that this particular one works. Right? There should be a large difference for us to decide that it is really good. So therefore, people decided that there is no significant survival benefit out of this particular drug. So even though the decision was like that, some people didn't want to just accept that in that way. They wanted to see further into detail, right? So see whether we can say something at least to the benefit of this particular, for the goodness of the drug, right? So what they did was, although the objective of the trial was clear, to compare mortality, to compare the mortality of this particular group versus the placebo group, researchers are often tempted to look deeper into the data. So therefore, they came up with a new question. The earlier question was to see whether there is a difference in the mortality rate, but now they changed their question. Right? They wanted to find out, maybe they say, maybe those who took the medicine really as we prescribed, then there may be an effect. Those who didn't take the medicine as we prescribed, probably there is no effect. Because whenever we prescribe something, always there is a group of people who really don't follow the instructions. Right? So maybe they were guessing probably. If we look at these 2 groups, those who are really adhering to the instructions, and if the other group, those who are not really adhering, because that information was also there, because they did this thing over 5 years. So they report most of the variables. So they knew that some people were not really adhering to this instruction, some people were really adhering. So now they wanted to compare these 2 groups. Earlier they were comparing the other groups who were taking the medicine and not taking the medicine. They were given the medicine and not. But now, out of those who are taking the medicine, they wanted to see the groups who are adhering and not adhering. Right? But now, earlier, the treatment group and the control group was randomly divided into 2 groups, right? Patients with a heart attack was randomly divided into 2 groups, and then the treatment group was randomly chosen, and the other group was given the placebo. So that was a complete randomized experiment. Now, they are within the experiment, they are now considering those who have taken the medicine, and then out of those, some people have decided they are not going to adhere. Some people have already decided they are not going to adhere. Now they are going to compare these 2 groups. When they compare these two groups, the results are like this. So what you mean by adheres is that if you're taking at least 80% of the pills, more than 80% of the pills, we call them adheres, otherwise we call them not adheres. So in this group, there's a placebo group also. So in the placebo groups also, some people who are taking the placebo, some people who are not taking the placebo. So in the treatment group, adheres and non-adheres, when you look at, there is a difference, of course. Adheres, 15%, only 15% died within the 5-year period. Among non-adheres, 25%. So if you don't look at this part, okay, so that shows that, okay, now it looks like the treatment is really working, right? Those who are really taking the medicine, less amount of people are dying, right? Among those who are not taking the medicine, large proportion of people are dying. Right? So that would have been the decision in that case. But that is again not correct. I will explain why not. But that could have been some decision taken by some people. But anyway, when you look at the placebo also, now even you can say that because these two are the same. Right? Adheres and non-adheres now, if there was a real effect of this one, this should have been even smaller. Right? Now, those who are adheres, that means they are thinking that they are taking the medicine, they are adhering to the placebo, this thing also reduced. These two numbers are the same, shows that definitely there is no effect in the drug. Right? So what happened here? Even though these two numbers are different, suppose for example these two numbers were also we didn't have these ones. Suppose we didn't have this one, we did only this thing, we looked at only adheres and non-adheres, and suppose we didn't have this one, can we decide that adheres, when you take the medicine correctly, then the death rate will be small? You cannot decide like that. Why? Remember here the adheres and non-adheres were not randomly divided into two groups. Right? So there was a group who is going to get the medicine. That was randomly divided, that group. But these two were decided by the people, whether we are going to take the medicine or not, were decided by the people, not randomly decided. So therefore, this difference, even if you didn't have this difference will not help you to say medicine works. Because these two, there may be several other confounding factors. Right? Those who decide to adhere to the medicine may be careful in other things also. Right? When they are taking food, maybe in other situations, their behavior, everything may be careful. So therefore, their death rate is small. Right? Not only because of that. That may be possible. Right? Because that is a particular type of people who have decided we will take the medicine continuously. But this is some people may be careless people, so they may die because of their carelessness, not because of not taking the medicine. Right? So this is an experiment where there is an example where even if you have a randomized controlled experiment, you cannot compare everything within that. This experiment was designed to compare the death rates among the people who are taking the medicine and not taking the medicine. Right? So that we can compare only those two things using this experiment. Right? As far as those two factors are concerned, this was a good experiment. That was an experimental study. But when you are comparing these two, it is not anymore an experimental study with respect to these variables. It's only observation because there is no randomness among the two groups. So therefore you have to be careful. Even in a controlled randomized experiment, you cannot compare anything you want. Right? So you should design the experiment in a way that you will be able to compare whatever the things you want to compare. Then you can compare and come to right conclusions about those things only, right? Not about anything else. So that's an important lesson to learn here. So the teaching point here is the this particular trial was well designed and a randomized controlled experiment. The valid comparison was between treatment and placebo, which showed no survival benefit from the treatment. However, investigators were tempted to look deeper and compare adherence and non-adherence. This comparison was not experimental anymore, it was now observational. Right? It was not randomized. Since patients decided for themselves whether to adhere or not, it became an observational study, not a randomized study. It created the illusion that the drug worked if taken properly, when in fact the same pattern appeared in the placebo group. So definitely in this case, because we have a placebo, so we can clearly see there is no difference. Even if there was no placebo group, we would have come to the same decision. So the lesson is, even in experiments, non-random subgroup comparisons can mislead. Randomization only protects the treatment versus the treatment versus control comparison. Right? So it protects from other confounding factors. So what is this experiment? This is another one. Yeah. So let's look at this one also. This is an example for a spurious association. So this particular Banneheka was a devastating disease in 18th and early 20th century, common among poor people in Europe and part of Africa and the southern United States. It caused severe physical and mental distortion, disability and premature death. So the objective of the study was to find out the variables associated, actually to find out the cause for this particular disease. But the study was an observational study. So design and investigation. This was to epidemiological observations, that is again observational study. They observed that sanitary conditions in affected households were poor and a lot of flies were abundant. Right? So in those houses where these particular patients were found, most of those houses were poor houses actually, and there were a lot of flies around in those houses. And they found out that there is a blood-sucking small insect in those areas, environments. So therefore, based on this observation, at the early stages, many epidemiologists concluded that this particular disease was caused by this particular infectious insects. Right? So there were a lot of evidence for that. Right? So therefore, they decided that this was caused by these insects like malaria or typhoid or whatever similar kind of things caused by some small insect. But then some people carried out some kind of more careful observational studies. Not only they observed the environment, they also observed some other things like what they eat, now how they exercise, and so many other things also were observed. Right. So in the 20th century, an American epidemiologist carried out a more careful observational studies, and experiments also carried out later. So they found out that in most of these households where this particular disease was existing, people were poor and they were eating a lot of the main food was corn. And they knew that this corn doesn't have some particular vitamins and some other minerals. One thing that was lacking in the corn was niacin. So most of these people, foods of these people were lacking niacin. Right? So therefore niacin came as a possible reason for this particular disease, right? So therefore, they further carried out some experimental studies and found out actually niacin was the cause, right? Lack of niacin was the cause of this particular disease. Right? So therefore, you can see that even though there is an association between the existing abundance of this particular insect and then the existence of this particular disease, that was not a real causation, right? Causation was not the insect. There is an association between the existence of this particular insect and the existence of the disease, but it is not a real causation. So with a careful study only, they identify possible variable, and then you can, in order to establish that is actually the causation, they have to carry out real experimental studies. Okay. So similar example here, ultrasound and low birth weight. So in this problem, earlier there were some experiments actually with some animals to find out whether there is an effect on the birth weight from ultrasound tests. So experiments on laboratory animals had shown that ultrasound exposure could cause low birth weight in animals. So if it was true for humans also, that would be a big problem, right? So because nowadays we run a lot of ultrasound before the birth, so if that causes low birth weight, that could be a problem. So that was a big concern during that period. So therefore, they wanted to investigate whether ultrasound examinations during pregnancy were associated with lower birth weight in human babies. So they carried out some observational study, not an experimental study again. So what they did was, an observational study was conducted. So some babies were they were exposed to ultrasound before the birth. There were some babies who were not exposed to ultrasound. So there were two groups, but they were not randomized or controlled. So what they did was, they measured the birth weight look at the birth weight of these two groups of children. They found out actually there is a difference, right? The average birth weight of children who were exposed to ultrasound were less than the average birth weight of children who were not exposed. Right? So it was a concern. Actually, it looked like what they observed in animals were prevailing in humans also. That was what was observed. But later on, they carried out further studies, and they looked deeper, and they found out there is some confounding variable, and therefore this apparent association is not a real association. What they found is actually those who did ultrasound were they did ultrasound because doctors found out some kind of weaknesses. Right? When they do some physical examination, they found out maybe there is some problem in the child in the womb. So therefore, they asked them to do ultrasound. Right? So therefore, most of the people who were exposed to ultrasound were actually had problems already. Right? So maybe the low birth weight was because of those reasons, not because of ultrasound. So therefore, they carried out later on. They carried out more experiments, and now we know that. Ultrasound is not actually reducing the weight in human, but actually that is more beneficial. If there are problems, we can really identify them. What they did was actually in that time, before doing the experiment, they in the analysis, once they found out that there were this confounding variable. Right? They did some adjustment in the analysis to remove the effect of this confounding variables. Right? As I mentioned earlier, there are different techniques. One technique is called regression analysis. So So in the regression analysis, they consider whether this exposing to ultrasound was a doctor's recommendation or not. That factor was included into the model, and therefore in the regression thereby you can adjust for that. But even after adjustment, still they show that there is a smaller average birth rate of those who exposed to ultrasound was small still. Right? So therefore the adjustment was not enough to consider, find out the actual thing. So later on then they did a complete randomized experiment and found out there was no problem of exposing to the other side. So you see these examples, you can see that there are so many things that you have to think about, right? Be careful when you are making decisions based on observational studies. So that was an experiment where the adjustment, right, we call it controlling for, we control for the confounding factors in the analysis. Sometimes that works, and thereby we can remove the effect of the confounding factor, and thereby find out the real effect of the variable. But not always, because there will be some other confounding factors which we don't know also. Right? There was one factor that they identified, but there can be some other factors also. Right? When we don't know those factors, we cannot measure them and we cannot include them in the regression model. So therefore, that doesn't work always. So in the next example, we have this is a famous example. We show that how to adjust. Sometimes it's easy to adjust and find out the real defect, right? So there are situations where we see something, and actuality is maybe completely opposite, or there may be no reason, no relationship. Sometimes we see an association between two variables, maybe positive association, but if we adjust for the confounding variables, we might see actually the relationship is negative, or maybe there is no association. So this is an example for that. Right? This phenomenon that there is an apparent association when you look at the whole sample together. Right? When you analyze the whole thing together, there is some association between two variables in one direction. But if you divide this sample into something called subsets, and if you look at the association within each subset, then we will see a different picture. Right? Maybe we see negative relationship now within each group, or maybe no relationship at all. Right? So there is a phenomenon like this. This is called Simpson's paradox. It's a paradox, right? Because we see one thing in one way, the other in another analysis we see a completely different thing. Right? So this situation, there is an example for the Simpson's paradox. In this example, what happened was there were some graduate students selected for the graduate studies in different departments of a university. Concerns were raised about possible sex discrimination in graduate admissions at University of California, Berkeley. The questions were whether men and women applicants were treated equally or not. Right? So there is a concern that men were favored when they were selected, and selection was biased against women. That was the general belief according to what they saw as an overall from the overall view. So they wanted to really study this situation and really see whether there is a real discrimination against the women. So determine if female applicants were being admitted at lower rates than male applicants, and whether this reflected any bias in the admission process. They wanted to find out that. So this was again an observational study. This was not an experimental study. The people came in different departments. So interviews were done in different departments separately. So students were selected by the different departments, and they were all together. In all departments, there were 8,442 male applicants and 4,321 female applicants. And out of those, if you consider all the students out of males, 44% of male students had been selected. Out of all the female students, only 35% had been selected by different departments. Altogether, this was the data. So there's a clear, large gap between the two percentages. Right? So that's why people initially believed that there was a discrimination against women. Right? There was a big gap, and the percentage for women was much lower than the percentage for men. So therefore, naturally, what one may say, okay, there is some kind of discrimination against women. So that's why the people are saying, okay, it is apparent that ladies have been kicked out. But then they did a further analysis. Now, these interviews were done separately by different departments. So they did analysis also in different departments. They found out the percentage of acceptance for men and women within each department. And this is what they saw. Right? So there are a large number of departments. Here they have given only the biggest numbers, right? Largest departments. Right? So subject department A, for example, say like mathematics, statistics, whatever major. So a total number of men came for interviews here for this one is 825. Out of those 62% was admitted. Here 108 women came for the interview. 82% women were selected. Right? So in that case, actually, women have been selected more than men, right? It seems like men are selected less. Men have been discriminated. And similarly here, 63% in department B for men, 62%, 63%, and 68%. So even though it's very similar, right? You generally you might say this kind of difference says there's no difference, right? Like even though number-wise this number is little large, probably it is not large enough for us to decide there is a real difference. Right? But anyway, at least this number is large, right? So that is again against their own direction, right? Earlier we were thinking that women were discriminated, but now it seems like men were discriminated. And the other department, this one is almost the same, this one is almost the same, this one is almost the same, this one is almost the same. So in this department there is no evidence of any discrimination against men or women. So in the other departments numbers were very, very small, and therefore they have ignored those things. But if you look at these numbers, so how would have that difference in the overall percentage be that large? When you see this, when you look at this department-wise, what is the reason? What could have been the reason?
So before calculating this, they would have calculated the ratios by dividing the admitted women divided by the total number of applicants.
Yeah, but they did also they take the total number of men who were admitted, divide by total number of men who came for the interview, and multiply by 100. So that is out of men, right? So that was the number. Out of men who came for, so there were 8,442 males who came for the interview. Out of that, 44% men were selected, and then only 4,321 female came for interview. Out of them, 35 were selected. So that's how they got it. And so they came from this data also. So why did the overall percentage of women became smaller than the overall percentage of men? Right. Now look at this total number of interviews in A and B, right, you can see that these numbers are the largest numbers. They were for men, right? Here, these numbers, even though the percentage was larger here, the total numbers were small, right? This is 82 out of 108. 82% out of 100. This is 68% out of 25. This is 62% out of 825 people. 63% out of 560 people. Right? So what happens has happened is here actually. They knew that. Now, if you look at these percentages, you can see that which departments are selecting more students generally, right, without any gender bias. You can see that these percentages are smaller than these percentages here and here in both. Right? So you can see that some departments are easy to get into, right, interviews. Right? Some departments are selecting most of the people who are coming for the interview, high percentage. Some departments are very strict, and therefore they are selecting only a small percentage of people who are coming. Right? So we can see that departments A and B are selecting a large proportion of people who are coming for the interview, whether it's male or female. Right? Percentages are very high. Right? So what happened here was, actually males were applying for those departments which are easy to get into. Right? Interviews වලින් දේශීය තේරෙන්න පුළුවන් department වල තමයි පිරිමි apply කරලා තියෙන්නේ වැඩි. So these numbers were large. And then the percentage, even though the percentage is smaller here, because of these large numbers here, when you calculate the percentage, overall percentage, these numbers play a large role. So the exam, the සංඛ්‍යාව වලත් මේක small. The percentage එක 82. එතකොට overall ගන්නකොට වෙන්නේ මොකද්ද? මෙතන percent සංඛ්‍යාව. මේ සංඛ්‍යා ටික නේද? You are adding the actual number of females selected out of the total number of females. Right? So you are not adding the percentages. So here, if you look at the actual numbers are small here. So because of the small numbers, the actual percentage of women who are selected became small. You can do this mathematics. I am not going to do it because you are mathematician. You can easily calculate it separately. But then the actual numbers you can find out actual numbers and you can yourself calculate the overall percentage. So you see that the overall percentage was smaller because here the actual numbers in these two departments who came for interview for the men was too much larger than these numbers. Metal small level percentage large metal සංඛ්‍යා උඩ. මෙතනදී මේ පිටා විශාල නිසා මේක percentage එක මෙතන අඩු වුණත් සංඛ්‍යාව විශාල. So ඒවත් මේ සංඛ්‍යා ටික නියැලෙන්නේ. So therefore when you are adding the total number of males selected, these numbers are large numbers. මෙතන කියන්නේ large numbers. මෙතන කියන්නේ small numbers. The total number of females selected is going to be smaller than the total number of males. Therefore, percentages is going to be high in the men. So that's what happened. So you can see that when you do the analysis department-wise, you can see the real picture. Right? You call this stratification. You stratify by the department. So you divide the whole population or sample in this case into different groups where each group is somewhat similar because within each department there was a separate interview. So therefore it is actually more meaningful to look at the percentage of men and women selected in each department separately rather than finding out the overall percentage of men and percentage of women who were selected. So if you did that experiment, then the conclusion will be, if you did the analysis like that and if you write down your conclusion will be completely different from what earlier was. Earlier they were saying that females were discriminated. Now you would say, even in some departments, males are discriminated. Right? In some departments there was no discrimination at all. So if you want to see that thing as an overall, then how can you get it? What they did was, they found out within males, they find out how many out of males how many were selected and out of females how many were selected. That was the calculation. But make a daging over the current.
Get the averages of the mean
Or
of the
total.
Yeah.
Right? So for example, here you have to find out something called the weighted proportion. Right? So make calculation. Within each department, you have the proportion. Then you can look at the weighted, right? So, for example, here, in the department A, the total number of people who came for the interview was 933. So, out of that, this many males were selected, this many females were selected. Now, the number of applicants. Right. So a more meaningful calculation that would have been used was something like this, right? Weighted percentage, average, right? Weighted average of the percentages. Right? Earlier we were just considering the overall average. Right? But if you consider the weight and the total number of people who came for the interview in each department like that, if you calculate this thing and then divide by the total number of people who came for the interview, these are the numbers that you get. This example shows you how to calculate for the mean. So when you calculate, this number is going to be 439 or 39%. That is the weighted average of percentages who were selected out of the mean for the mean. And similarly, weighted average of admission rate for women was 43% now. Right? So the numbers are completely in the other direction. And this calculation actually shows the actual picture what we saw in the stratified analysis. Right? So this is more reasonable value because it tells you earlier also we saw that in some departments actually males were discriminated, if you want to use that word. There were less amount of males selected than the females. And in some departments, there were no difference. So, therefore, overall, actually, if there is any difference, we should say males are less selected than females. And these two numbers actually reflect that story than the other one. The other one is actually. So, that tells you that there are situations where the overall picture doesn't tell you the truth. If you stratify and analyze within each stratum, you will see the correct picture more clearly. So that is another thing that you have to be careful when you are doing observational studies. Right? So this situation, this earlier observation, right, and this result together is called the Simpson's paradox. Directly we see some association, but if you do it by strata, then you will see a completely different picture. Right? So that's called Simpson's paradox. So careful control for confounding variables. So in this case, the confounding variable was the selection of the department. Right? So men were selecting the departments which are easy to get into. So therefore, most people are going into those ones. So therefore, in those departments, the number of females were less, but so that contributed to small number of small percentage overall in the females. Okay, so we are coming to the end actually. So I'm not going to give you written exams or written homework yet. Probably next week we'll start something. But for the moment, please go through there are some, there's a summary and overview in each section, so please read that. And in addition to that, so there are some problem sets for which you have answers. Right? So we have here, for these two chapters, we have one problem set called set A. So first see whether you can answer them without looking at the answers, and then check your answer with the given answer. Right? So please do that. That will help you to think a little bit. And then in the next week there are some review questions also. for which you don't have the answers. The answers are not in the book. So please go through those also. Next week we will discuss answers to those questions. So I'll see what your answers are. Of course, you can use AI also to get some idea. Doesn't matter. You have to learn somehow. But think first, and then maybe you can check your answer with AI answer, and so on. We will discuss those things.